Okay, so let's start. So just to give you an idea, do we have a pointer? Yeah, maybe you can bring it. Okay, just to give you an idea, we covered microarchitecture fundamentals before Easter. Last week is Easter, of course. And then we covered pipelining, and then we covered a lot of issues in pipeline processor design, data forwarding, bypassing, control dependence prediction, basically control and data dependence handling, including fine-grained multi-threading. Do people remember all of this? Hopefully it's good. Yeah. So many issues in pipelining. So basically, pipelining instruction execution introduces a lot of issues, as you have seen. And we've tackled some of those issues. We're going to tackle more of those issues, actually, soon. Today, precise exceptions. How do you maintain state? How do you recover state? That's going to be important, especially when you're pipelining instructions and doing multi-cycle execution, as we will see. And hopefully today, later today, we will start with out-of-order execution, which is dynamic instruction scheduling. And then I don't know if we will cover load store handling, which is the most hairy part of a microprocessor design today. But maybe I'll give you an additional lecture just for your information. We'll see. Readings, we'll still continuing. You've seen these readings. How many people have read the Smith and Sohi paper? Anybody? Don't be shy. Okay, I see some hands. That's great. Do you like it? Is it good? So, okay. Yeah, this is an introduction to superscalar processors. Your books don't do a great job, unfortunately, in this. It's a bit sad that books don't cover it in enough detail. Okay. Anyway, we'll cover it in more detail. So remember, this is where, can people hear me in the back? I hear an echo. Is it only me? It's all good? Okay, if it's all good, no problem. And it's all good online, it's also no problem. So this is where Mohammed kind of started, but he didn't finish because he didn't have time. We're going to talk about preserving sequential semantics and von Neumann architectures especially. And this is a slide that Mohammed mentioned. But basically, imagine a system where not all instructions take the same amount of time in the execute stage of the pipeline. This is possible because you can have multiple different functional units that you send the instruction to. One instruction goes to an adder, another instruction goes to a multiplier, another instruction goes to a load unit, for example. And your pipeline, or at least the back end of the pipeline, after an instruction is decoded, may look like this. So this is, we're going to see machines like this. All of the machines are like this today, basically. Some instructions may take only one cycle. Some other instructions may take 4 cycles. Some other instructions may take 8 cycles. Some other instructions may take hundreds of cycles, let's say, in the execution. And the functional units may be pipelined or not pipelined. So basically, all of the principles that we discussed can apply to the execution unit also, pipelining. Now, if you actually have a system like this, you can let independent instructions start execution on a different functional unit before a previous long latency instruction finishes execution. For example, you fetch an instruction, you decode it. It happens to be a multiply, and this multiply is going through the multiply pipeline. And then you fetch an instruction, another instruction, and decode it. It happens to be an add instruction, and this add instruction is independent of the multiplies. Pipelining says that you should be able to continue execution of this add instruction, which is independent, and you send it to this functional unit. But then this add instruction finishes quickly, whereas the multiply is still continuing. Now we have a problem, right? Multiply takes 4 cycles, it's older. Add instruction takes 1 cycle, it's younger. What do you do? If the add instruction finishes, do you write its result to the register file? Well, that was the question Mohammed asked last time. And that's the question over here, basically. How do you arbitrate the writing of the results to the register file so that you actually preserve the semantics of the von Neumann model, which is really sequential instruction processing, right? So based on what we've discussed with the von Neumann model, you should not let a younger instruction write its result into the register file or memory, because otherwise you'd be breaking the sequential instruction semantics. And that's absolutely true. In fact, this becomes even more problematic with what we're going to discuss, which is exceptions and interrupts, because it makes these out-of-order writing of the results visible to the programmer if you do the wrong thing, if you break the sequential semantics, basically. So let's take a look at this example that we covered briefly last time. Essentially, instructions can take a different number of cycles in this execute stage. For example, we see the difference between an integer add, which is 1 cycle in the execute stage, and integer divide, which is 8 cycles. I just want to amplify this. In existing processors, a divide can take 40 cycles, maybe 50 cycles. An add can take 1 or 2 or 3 or 4 cycles, basically, at high frequencies. Now, if you look at this picture shows the execution of instructions. You fetch, decode, and then you dispatch, and we're assuming all of the instructions are independent of each other over here. That's why you have a nice pipeline that's filled. But some instructions take 8 cycles in the execute units, divide, for example, and the next add instruction takes only 1 cycle and writes its result into the register file, happily. Next instruction also writes its result into the register file. Next instruction also writes its result into the register file in consecutive cycles. But this poor instruction has not written its result into the register file yet. So if you remember the last lecture, Mohammed asked you the question, what is wrong with this picture in a one-Neumann architecture? Essentially, this is what's wrong. This write violates the sequential operation semantics, right? Because this instruction has written its result into the register file before a prior instruction has completed. That's true for this instruction as well, this instruction as well, and this instruction as well, and this instruction as well. All of these instructions violated the sequential instruction semantics. We should not have written their results into the register file, basically. Makes sense, right? Okay. So that's a legalistic answer, as usual, right? This is a contract between the hardware and the software, and the programmer assumes that these instructions should not write their results into the register file before a prior instruction is complete. Now, that's what we would expect. But then you should always ask the next question: why does it make sense? Why do we have this legal, let's say, contract, if you will, between the hardware and the software? And that's basically going to be because of precise the notion of exceptions. Let's take a look at that. Basically, the problem really happens if this divide is not supposed to finish or has some problem, let's say. And one problem with divides could be you could be dividing a number by 0, right? And if you divide a number by 0, what do you get? For those of you math gurus out here, anybody? You get an undefined value, or not a number, basically, right? You should not divide by 0, essentially. That's called an exception. Basically, it's an exceptional condition that the instruction produces, and it may happen that the value that you're dividing by is 0. And if you actually have this sort of problem, the program should not continue. The program should exit with an error. Or the programmer figures out that there's a divide by 0 and does something else with the program. The programmer can catch this exception, actually. There are mechanisms that you can actually add to the program where the programmer catches that you're dividing by 0 and does something else, goes and fixes up the value, for example. If you're programming, actually, you may know this. How many people you have used try-catch blocks or catching exceptions in programs? Okay, there you go. Now you know what this is about, basically. You could catch exceptions at a higher level, but they get translated to these lower level exception catching mechanisms. So basically, if you have an exception, how many people have caught the divide by 0 exception? Okay, some of you. And you would like to catch that, right? Yes, you don't want the program to continue. But when you catch that, you don't want the later instructions to have written their values into the register file, because otherwise you'll have to be dealing with a mess. Because something is completed out of order, right? When you catch that, you really need to know what your state is in the program so that you can recover back and do something better with the program, essentially. Okay, so that's basically the reason that's one of the major reasons why we want precise exceptions. So, okay, I mean, Mohammed, I think, showed you pictures of the analogy that I used last year when I was actually teaching this course. Basically, I see this tram as an exception-causing instruction that's had some failure, essentially. And you can see that that's tram 11, I think. Well, maybe not here. And then there's another tram that's delayed because this exception needs to be handled for this tram to continue. And this second tram may have nothing to do with the first tram, basically, right? And then there are other cars that are delayed, as you can see, that are because of this exception-causing instruction. And you can see that that's tram 11, and the other tram is delayed in the back. And then you can see that this is still going on. I'm walking, as you can see, and it's still going on. And then finally, the instruction is resolved and exception is handled, and then the instruction can continue. I don't know if this was the exception-causing instruction. This may need to be relabeled. But basically, you can see that because one instruction or one tram caused a problem, another tram in the back could not move, right? And this is an exceptional condition. I'm going to use this to motivate something else later on. But here I'm motivating an exceptional condition. It may not be the perfect analogy, but it's really an exceptional condition. Maybe the tram had a power failure. Maybe one of the door was not operating, right? That was a problem with that particular tram. And the later instruction could not move on. Okay, so the analogy holds in the sense that exceptions or interrupts are actually unplanned changes or interruptions in program execution. So for the tram, it was an unplanned wait over there at the station. It could have been somewhere else also. But in programs, this also happens, basically. And there could be two major reasons. This could be due to some internal problems in the execution of a program. Essentially, this is called an exception. Divide by 0 is internal to the program, right? This divide instruction is part of the program, and it's got a divide by 0 error. It just happened that you're dividing by 0. But it could also be external, completely external events that need to be handled by the processor. These are called interrupts. These are fundamentally very different. Although in a von Neumann architecture today, the handling of them are very similar. But I want to make sure that you understand the fundamental difference, because these are really different concepts in the end. Because handling of them may be different in different architectures. That's the reason why it's good to understand that these are different. So external event could be, for example, a power failure. You have a power failure, in the tram, the example doesn't work, but in the machine over here, you're executing a program, and then you have a power failure because your battery ran out, right? That's an external event to the program. That has nothing to do with the program that you have written as a programmer, and you cannot really deal with it, right, as a programmer, because it's completely external while your program is running. But the machine has to deal with it, because if a program is running while the power failure is coming, then that program should not continue, but should go into a state where it could be continued later after the power failure is handled in some way. So that's the example of an interrupt. Another example of an interrupt is a network packet, for example, coming from an Ethernet controller or the wireless controller, and you need to handle that network packet processing somehow. That's an external event coming. And if your program is completely independent of that network packet, that has nothing to do with your program, clearly, right? But your machine needs to be interrupted to process that packet in some way so that you can actually make progress in the entire system, right? So that's the difference between exception and interrupts. And these are actually going to, we're going to go into a little bit more detail in terms of how they're different. But both of them in the end require stopping of the current program at some point. As we will see, they're different in exceptions and interrupts, and also types of exception and interrupts. But when you get a divide by 0, for example, you got to stop the program right away. So exceptions are actually very critical. You need to immediately stop the program almost. And then you need to save the architectural state somewhere to make sure that you have not lost any data in the program. And then you need to transfer the state or switch to some other control. This is called handling the exception or interrupt. You have a special interrupt or exception handler that handles the interrupt. For example, you can have an exception handler that's written by the programmer to handle divide by 0. You can have an exception handler that's written by the system designer to handle potential power failure, battery running out. Another interrupt handler for packet processing, for example. A packet has arrived, or somebody pressed the keyboard. How do I handle that? So that's a keyboard interrupt handler, for example. So there are many, many interrupt handlers that you need to do. And then, if possible and makes sense, you return back to the program execution. This may or may not be possible, clearly, right? But this is something we try to do if the program is restartable or continuable, depending on the nature of the exception or the interrupt. Does this make sense? So basically, this is how we handle exception interrupts in a von Neumann architecture. But interrupts fundamentally can be handled slightly differently, and we may discuss that later on. For example, if remember, we discussed the notion of data flow in the past. Data flow really doesn't have the notion of an interruption, if you will. Everything is a data flow graph, and you need to make sure that interrupts are actually handled like a data flow graph as well. Okay, maybe I don't want to go into that right now. Okay, so let's take a look at examples. I've given you some examples, but exceptions are internal to the program. It could be divide by 0. It could be a value has overflowed such that it cannot be represented by the number of bits allocated to a register, for example. It could be an undefined opcode. Basically, the machine fetches a binary value that's not an opcode, and it tries to decode it, and it gives up. That could happen if someone has written a wrong program, let's say. It could be some access protection or general protection exception. This may happen when a program is trying to access a memory location that it doesn't have permissions to access. It's actually very useful to implement these exceptions so that you implement some basic security primitives in your system. And we're going to talk about that when we talk about virtual memory. But hold on to that, because we have not been talking about memory a whole lot so far. In lecture 25 or 26, you will see that. It could be a page fault, and again, we'll see that when we talk about virtual memory. Page fault is actually when you're trying to access a memory location that's not inside the physical memory. Again, this is intrinsic to the program. A load or store instruction may trigger this page fault, but it's not in your physical memory, and we will see why it may not be in your physical memory when we talk about virtual memory, so hold off on that. But it could be on disk, and then there needs to be a page fault exception that's handled by the operating system, and the operating system brings the page or the data that you need from the disk into the physical memory to make sure that your program actually works. So we have not talked about that, so if you've not understood anything related to the page faults, that's fine. We'll cover general protection and page faults later on. So you can see that these exceptions can be internal to the program. Some of them can be extremely bad, like potentially divide by 0. You get a 0 value divided by it, you didn't anticipate it, and you don't have a handler for it to fix it, then the program basically needs to be halted, stopped, right? But page fault is actually useful because that enables you to use memory that is bigger than your physical memory, and that enables larger programs essentially. Okay, these are, as you can see, all internal to the program, related to the program. But interrupts are completely unrelated. For example, an I/O device, a keyboard, as I mentioned earlier, or a camera, may need to be may need some service. And it basically sends a signal saying that I want some interrupt handler to be executed so that you can take my video feed, right? Or whatever, network, right? It could be more periodic, system timer, for example. Periodically, operating system may have a timer that basically interrupts the processor and does some maintenance tasks. It could be power failure. This is clearly quite high priority. And then it could be machine check. It's called machine check, but there could be some error inside the system. This gets detected, and you normally don't want to move the system forward if there's an error that gets detected. You want to handle that error, and that's why it's called a machine check. Check the machine, basically, to make sure that there's nothing wrong in the data values, etc. Right? So these are just examples, and you can come up with many, many others. So is this distinction clear? Exceptions versus interrupts? Okay, great. Now, basically, the main distinction comes from the cause. Exceptions are internal to the running thread. Interrupts are external. As a result, this determines when they are handled as well. For example, exceptions are usually handled when they're detected and known to be non-speculative. So non-speculative means the instructions that are actually supposed to execute, because we have some speculative instructions that are not supposed to execute yet, right? Because we're doing branch prediction, remember? The control prediction that we discussed in a pipeline processor. We're going to do more of that in a couple of lectures. So you need to make sure that you really need to handle that exception. It's a true exception. And also, usually you need to handle it right away. Interrupts, on the other hand, can be handled when convenient, meaning some network packet is coming, for example. You don't have to immediately handle that. You can buffer it for some time and then handle that after some point. So there could be some interrupt handling latency. So it really depends on the nature of the interrupt, except for very high priority ones like machine check or power failure that usually need to be handled immediately, because if you don't handle the power failure right away, you may actually lose some data, right? Because there's at least one program, let's assume that there's at least one program is executing in your processor, and your battery is about to fail, and you get the signal from your battery saying that I'm going to lose power. You'd better save some of the state of the program so that you can actually restart the program later on when actually power comes up. If you don't handle it at a very high priority, you may lose that opportunity to save the state, basically. Okay, so and then the priority of the interrupt versus exceptions is different because the cause is different. So the priority of the exception is essentially the same as the priority of the process, because it's really internal to the process. On the other hand, the priority of the interrupt really depends, as I just mentioned, right? Power failure is very high priority. It's actually perhaps perhaps the highest priority thing in the system. It doesn't matter who's running what. I got to handle this power failure, right? As opposed to a network packet received. Well, maybe it's not that important, right? Because there are other mechanisms that are also handled in the network. Maybe somebody's going to retransmit that packet, right? If you actually, especially if the higher level protocols cover for that packet loss, if you actually lose a packet in the end. Ideally, you don't want to lose a packet, but this is not. This also shows that it's not that critical. There are other ways of handling a potential packet loss if you cannot deal with it for whatever reason, because the machine may be overloaded. Okay, and then the handling context, I'm not going to talk about this, well, maybe I'll talk about it. But basically, exception is handled in the context of the process. That's why as a programmer, you can try and catch an exception and fix the exception, handling exceptional situation. Whereas the handling context of the interrupt is a system, because it has nothing to do with the process in general. So interrupts are actually handled mostly by the operating system, whereas exception handlers can be written by the programmers. Although there are vanilla exception handlers that are provided to the programmers if the programmer doesn't supply their own exception handler in exceptional conditions. Okay, so I think I've made this clear. So, okay, what does precise exceptions or interrupts mean? So for the purposes or the rest of this lecture, I'm going to keep exceptions and interrupts very similar because they're handled similarly in a von Neumann architecture. Maybe if we have time, we can discuss the differences at the end. But what does it mean for them to be precise? This basically means that you should obey the von Neumann model sequential semantics that we have learned several lectures ago. Essentially, the architectural state, which consists of program counter, memory, and registers, should be consistent or precise when the exception and interrupt is ready to be handled. So what does that mean? This means because of the sequential instruction semantics, you have an exception causing instruction. All previous instructions in the program order should be completely finished, retired. That's also called retired, meaning that they should have updated the architectural state completely. And no later instruction should be retired, meaning should have updated the architectural state. So you should really have a clean slate between the exception causing instruction and later instructions, if you will. So retire, commit, just to define it. You finish execution and update the architectural state. That's the definition. Some people also called graduate. I don't like graduate that much, but and mostly retired and commit is used. So let's take a look at this example. You have a bunch of instructions. If you want to look at the precise state, if this divide, for example, if you want to look at the precise state, if this divide is supposed to cause an exception, there should be a precise state over here, or if this add. Basically, you could draw this precise state between every instruction. This means that all instructions before the divide have finished and no instructions after the divide have finished. And then the divide can be handled, the exception at the divide can be handled. So why is this useful? Because the programmer now can make sense out of the program, right? If this divide causes an exception, the programmer knows that R3 is not updated with this add, R2 is not updated with this divide, R7 is not updated with this add. Basically nothing after this divide has finished, and everything before this divide has updated the state. So they can actually reason about what happened and how this potentially can be fixed. Okay. If you have questions, feel free to interrupt. That's an interrupt, basically. If I have a problem, then I will take an exception. So I mean, this is my exception, for example. I handle my exception because my mouth tells me that I need to drink some water. Could be called the dry mouth exception. But your interruption could be, I don't know, a shouting student exception, right? A shouting student interrupt, right? Okay. Okay. So basically, how do we check for? We're gonna. So in the end, you should check for and handling exceptions in pipelining. How do we check for and handle them? In the end, there are multiple steps we follow, right? When the oldest instruction is ready to be retired and is detected to have caused an exception, the control logic needs to take some actions. Right? So what is this action? First of all, it needs to ensure that architectural state is precise, like we defined earlier. Register, file, PC, and memory. Remember, architectural state is always like that. You need to ensure that all younger instructions are flushed from the pipeline. Remember, we have a pipeline. We have the oldest instruction that caused an exception, because you need to check the oldest instruction because all of the younger instructions are speculative. So we have not defined this very well, so I'm going to talk about this quickly. So if you have a pipeline, the oldest instruction that's ready to write to the register file is the only one that is guaranteed to execute. All of the younger instructions are speculative because the oldest instruction may cause an exception, right? So you should make sure that the oldest instruction is the one that's to be checked for retirement. And if it causes a problem, meaning if it's going to have an exception, or if there's an interrupt that you need to handle at that point in time, you ensure that the architectural state is precise and you flush all the younger instructions in the pipeline so that they do not update the architectural state. Flush means, we've seen the pipeline flush, you actually invalidate the registers, right? Pipeline registers, as we've discussed. And then you need to save the PC and the registers as specified by the ISA. So the instruction set architecture needs to specify how to handle an exception or interrupt, because this is really necessary for someone to write software, right? Either system software or regular software. So there needs to be some support in the controller. The control logic takes the program counter and the registers and saves them to some place specified by the ISA. Usually it's part of the main memory stack, as we will see briefly. And then the control logic redirects the fetch engine to the appropriate exception or interrupt handling routine. Now, what does this mean? Basically, let's say you have a divide by zero exception. This control logic caught the exception because it saw that there was a zero you're dividing by. And then it basically completes all of these three steps. And then basically redirects the PC, sets the program counter to an exception handling routine. And that exception handling routine can be a specialized routine for divide by zero. Or it could be a general routine. Basically, you always switch to a particular location that's usually in the system code. And you start executing that system code, and then there needs to be some place where you check what kind of exception am I dealing with. Okay, there are multiple approaches to this, which I'm not going to go into. That goes into more detail than needed, if you will. But there are different kind of interrupt or exception handling architectures also. Whether you go to a general purpose routine and then check the cause, or whether you immediately go to a specialized routine. There are trade-offs, but we're not going to go into that. Does that make sense? Okay, so as I said, interrupts and exceptions need to be defined in the ISA. These are part of the ISA. They have to be implemented by the microarchitecture. And this is actually a very beautiful description from Intel's x86-64 ISA manual. These ISA manuals are actually very beautiful books, in my opinion. Sometimes they're very hard to read, but sometimes they're beautiful like this. Let's take a look at one example part over here. I'm actually going to read it. Because these folks actually are very good at distinguishing between interrupts and exceptions nicely. Not all ISAs do, unfortunately. But let's take a look. And also they describe it nicely. When an interrupt is received or an exception is detected, the currently running procedure or task is suspended while the processor executes an interrupt or exception handler. When execution of the handler is complete, the processor resumes execution of the interrupted procedure or task. The resumption of the interrupted procedure or task happens without loss of program continuity, unless recovery from an exception was not possible or an interrupt caused the currently running program to be terminated. So it's not always possible to get back to the program, basically, for various reasons that are not detailed, but you can guess what they are. Okay, so let's go back into this. Why do we want precise exceptions a little bit before we start adding more complexity to our machines? So as we discussed earlier, one of the reasons is legalistic. Semantics of the von Neumann model ISA specifies it, so you need to obey that, right? And that's absolutely true. But this is kind of a cop-out answer in a sense. Then the next question becomes, of course, why does the von Neumann ISA specify it, right? Because it's easy for the programmer, basically. That's the answer. Then the next question is, why is it easy for the programmer? And then we're going to answer that in the next bullets, if you will. But let me mention that von Neumann model specifies precise exceptions, but data flow model doesn't specify any such thing, right? Because in data flow model, there's no ordering of instructions anyway. Exceptions still happen. You may have a divide node. Remember the nodes in data flow, these bubbles? You may have a divide by zero. An exception happens. Then how does the programmer debug that thing? It's a huge data flow graph. You don't know what is executed and what is not executed, right? And this is exactly the reason sequential semantics has been very successful, whereas data flow at the ISA level, visible to the programmer, has not been successful, because when you get an exception, for example, it's very difficult to handle it in a data flow machine. It's very difficult for the programmer to delineate a state, basically. Whereas precise, von Neumann is very easy. So that's the reason, actually, of the next few bullets, if you will also. Basically, this aids software debugging. Because you know exactly which instruction finished and which instruction did not finish. And there's a clean state sequential execution. So when an exception happens, you can basically go and debug it very easily. Now imagine, in contrast, we did not have precise exceptions. If we go back to this, where is it? If we did not have precise exceptions and I should have gone in a faster way. Okay, there you go. These instructions have written, when this divide instruction generated a divide by zero exception, these instructions may have written their values. Some other instructions may have written their values. Now, if that's the case, the programmer has no idea, right? there's no contract, if you will. The programmer needs to somehow figure out what has happened. They need to reconstruct how the machine has executed the program. And this is what we don't want programmers to deal with. The programmer should not worry about what instruction is executed in the machine and what instruction did not finish, what instruction updated the register file and what instruction did not update the register file. That's why we have this precise exception semantics that says, programmer, you don't need to worry about what the machine did. I'm going to guarantee you that this instruction that caused the exception, after this instruction, no instruction is finished, and all of the instructions prior to this instruction have finished. So that's the reason for the sequential execution semantics, actually. And that's perhaps the major reason, most major reason, let's say. Okay, so it aids software debugging, basically. Now, can you debug it without this? Of course you can, but you'll pull your hair out probably for days and days. Basically, it'll be hard. You can do anything in the end as long as you know what's happening, because this is a deterministic system. In the end, you can reconstruct what has happened, but it's extremely costly and expensive. In fact, one of the processors IBM built out of order execution, IBM's early out of order processor, we're going to talk about that in the next lecture, or maybe later part of this lecture. They basically chose not to have precise exceptions. They basically said, we're not going to support precise exceptions in our machines, and that machine did not get used much. Essentially, that was a very bad business decision in the end. It was a beautiful machine, but didn't support software debugging easily. Okay, so there are other reasons why you want precise exceptions. You can enable easy recovery from exceptions, as we discussed. You can easily say, flush all of the instructions in the pipeline. They're not important because you have a precise state, right? And then you can come back to the program counter. You don't need to fix up any state, basically. I'm going through this relatively quickly because there are actually other details that I don't want to discuss necessarily. You can restart the process relatively easily. Basically, you know exactly where to start the process, right? This program counter calls the exception. And if I restart at the same point, I'm going to execute this instruction, the next instruction, the next instruction, the next instruction, and I'm guaranteed that none of them already executed, right? If some of them actually had executed, then you have to deal with that somehow. And it's a mess, right? But now you're guaranteed that none of the later instructions are executed, so you can actually restart the process at the program counter that has caused the problem, right? Or that you kicked out of the machine, let's say, at that point in time. And also there are other benefits. This is actually very similar to debugging in a sense, but for example, you may have an unimplemented opcode or software implement opcode. You didn't implement this. Let me give you an example. For example, you don't assume that you don't have a multiplication instruction in your ISAs, which may happen. Initially, MIPS didn't have it. And you say that I'm not going to implement multiplication, but I'm going to, in hardware, but I'm going to have an instruction. And this instruction will be executed by the software. What does that mean? Whenever I see a multiply instruction, I'm going to generate an exception. And this exception is going to take me to an exception handler that's going to do exactly multiply using add, shift and add, basically, right? And then you're going to return from the exception and get the value. That's perfectly possible. That's actually done with complicated instructions. Multiply, of course, is present here. But for example, you may have a floating point operation that you don't want to implement in hardware because hardware is costly. You basically, whenever you see a floating point operation, it calls an exception. You go into an exception handler that executes a floating point operation using the integer operations. It's lots of instructions, but you can do it. So basically, this way, you can actually implement some instructions that are actually not inside the hardware. And again, with precise exceptions, you can do that. With imprecise exceptions, it's very difficult to do because you're not guaranteed what, you don't know what's executed and what's not executed. Okay, any questions? Okay, I've motivated a lot, but I think this is really important because this goes to the core of the hardware-software interface also. So we kind of pulled back from we were looking a lot into microarchitecture. Exceptions and interrupts actually pull us back to the hardware-software interface. And exceptions and interrupts are actually going to be a lot more important, especially for cyber-physical systems. Like these systems are not that cyber-physical, but if you actually have things like, I don't know, the drones, for example, or brain-machine interfaces, they're all cyber-physical. It's all about interrupts from the outside. So a lot of the processing that you do is actually based on what's coming from the outside. So handling these interrupts actually is going to be more important. And there'll be a lot of exceptional conditions also. Okay, so now the question is basically, this is a good thing. We want precise exceptions. How do we ensure it? how do we make sure this works in different types of machines? So we're going to take a look at single cycle and multi-cycle relatively quickly, and then we're going to talk more about pipeline. So in a single cycle machine, instruction boundary is the same as cycle boundary, so the problem doesn't exist, if you will. An instruction is guaranteed to be finished in one cycle, so there's no possibility of violating sequential execution semantics. Because one instruction is finished, the other instruction doesn't get started before the previous instruction finished. So there's no problem here. In a multi-cycle machine, it's not that big of a problem, but we need to do something special, basically. How do we actually go to the interrupt or exception handler? So you need to add special states in the finite state machine. Remember the finite state machine that specifies the behavior of the multi-cycle program? You need to add a special state, well, multiple special states to the control finite state machine that lead to the exception or interrupt handlers. I'm going to show you some pictures, but your book actually covers this nicely, let's say. It doesn't cover what's really interesting, which I'm going to cover later on. But basically, your book has a nice treatment of exceptions in a multi-cycle architecture. But it can be used for interrupts also. Basically, you switch to the handler only at a precise state. What does that mean? Before fetching the next instruction. Once you finish the previous instruction, check for the interrupt, check for the exception or interrupt. And if there's an exception or interrupt, go to a special state, which is the exception handling routine. We're going to take a look at that. So this is actually what's how your book modifies the multi-cycle data path that we studied. Basically, you have you need to add some special data path components like EPC register your book adds, which holds the exception causing PC. This is the program counter that caused the exception. Remember the divide instruction potentially. Cause register holds the cause of the exception. I think in this particular case, there are two possible causes. One is overflow in the ALU. Basically, the value that's generated as an ALU result cannot be represented with the number of bits that are in the word. And then there should be another exception over here. I think it's an undefined opcode exception, which is not visible over here as far as I can see, but you will see it in the next slide. So basically, there's a cause register, and then there's an exception handler that starts at this address in the system. So this is a general purpose exception handler. So what happens is when an exception happens, the cause is set, and the exception causing PC is set, record an EPC, and then the machine jumps to the exception handler, and this exception handler later checks what kind of exception is it by querying this EPC, this cause register. Okay, does that make sense? So you need to modify the finite state machine. If you recall several lectures behind, this was the finite state machine that we constructed actually. Most of this we constructed for a multi-cycle MIPS architecture from your book. But basically, that finite state machine that we constructed is now modified to support two exceptions, overflow and undefined instruction. Now let's take a look at the undefined instruction. So this is the fetch state. If you remember, you go into the decode state, and then there's some control signals clearly. If the opcode is others, meaning it's not defined, it's not any of those things that you're supporting, then you go into a special state. The state 12 is called undefined. And the special state does something interesting. Basically, it sets the PC write signal. It sets the interrupt cause to 1, meaning it's an undefined instruction interrupt. Well, exception. It sets the cause write to 1 and EPC write to 1. What does that mean? Basically, cause write is you're writing the exception cause, and then EPC write is you're writing the program exception EPC register with the program counter that actually is pointing to the undefined instruction, right? And then PC source is 1-1, and that means that if you look at this data path modification, you jump to the exception handler. So after the state, the next program counter is the exception handler. So you've jumped to some location in the program that's actually dedicated to the system, and system is going to execute the exception handler. And it's going to check what kind of exception happened. At this point, it has no clue, but the exception is recorded in this cause register. So as a result, MIPS architecture adds a special instruction, MFC0. It's a terrible name. You can read the book to figure out what that is, but it's, I think, controller 0, coprocessor 0. I forgot these two other ones. Something from coprocessor 0. It's a messy name, basically. But basically, it's used to copy the exception cause into a general purpose register. basically, what it does is this special instruction takes this cause and copies it into a general purpose register. I'm going to show the pipeline, not pipeline, the modifications to the data path after this. So this is how the exception handler can figure out whether it's an overflow or an undefined instruction, essentially, and then it can take some action accordingly. If it's an undefined instruction, of course, you have to stop the program, right? But you may actually do some bookkeeping saying that, oh, there's a particular instruction that people keep using as undefined instruction, right? Who knows, right? The system can actually do a lot of recording, for example, right? Okay, so that was the example of undefined instruction, undefined opcode exception. Let's take a look at another exception over here. So this happens when you have an R-type operation. And when you have an R-type operation, you have the ALU result over here. If there's an overflow, you go to the state. If there's no overflow, then you basically go to the write-back state. So if there's an overflow, you go to a special state where you don't write to the register, as you can see, right? So this is the overflow. And here you do a very similar thing. You set the program counter source to exception handler. So the next instruction to be executed is the exception handler. And then you write the program counter. Interrupt cause or exception cause here is the overflow, which is 0. And then you cause write and EPC write. So basically, these two states are very similar. They're basically setting up the exception handling mechanism so that you jump to the exception handler and then you have the correct exception cause recorded in the cause register, which we defined already over here. Does that make sense? So basically, all of the possible exceptional conditions in your system will need to be encoded in your finite state machine so that you add these states that take you to the exception handler in a graceful way. Graceful may meaning what we have discussed earlier. You should not update the architectural state with the exception causing instruction. You should not do this. You should do this because there's a problem with the instruction. And you should make sure that you go to the exception handler, which will do some stuff. Okay. So you can see there's more that needs to be done. This is actually needed. These are the modifications that are needed to take the exception cause in this cause register and place it into a general purpose register. So we're complicating the data path, right? You can see that this data path supporting MFC 0. So let's take a look at this. Let's read this from your book. Basically, in summary, an exception causes the processor to jump to the exception handler. The exception handler saves registers on the stack. This is specified by the MIPS architecture. Then uses MFC 0 instruction to look at the cause and respond accordingly. When the handler is finished, it restores the registers from the stack, copies the return address from EPC to blah, blah, using MFC 0, and returns using jump register to K0. Basically, what this is saying is, if the handler is finished successfully, you return back to the program. Because you saved the program counter, right? You basically, this is the exception causing PC. You return back to the exception causing PC, assuming you have gracefully handled the exception. This doesn't always happen, of course. If you are not able to return to the program, what the exception handler does is it kills the program. It says, I cannot execute this program. It has an undefined opcode, etc. Right? It can skip the undefined opcode also, right? That's a potential fix to the problem, but it doesn't always work semantically nicely. Okay, any questions? Okay, so you can read about this in your book clearly. Now, what I'm going to talk about is more advanced, and it really happens when you have this notional multi-cycle execution. This brings about more complications. It doesn't happen in this sort of pipeline. Here, you need to have pipelining plus multi-cycle functional units. Basically, instructions can take different number of cycles in this execute stage, such that some of them actually complete execution out of order. Now, if some of them complete execution out of order, you should really not finish those or update the architectural state out of order. That's the problem, basically. Then the question becomes, what do you do? Right? These instructions are finishing early compared to prior instructions, and clearly you should not update the architectural state based on everything we discussed. Okay, so what do you do? One thing you can do is this. Basically, don't make sure that this problem doesn't happen. Meaning, if you have a particular instruction that takes 8 cycles in the execute unit, make sure every instruction takes 8 cycles in the execution stage. This is the worst case solution. It's kind of similar to the single cycle architecture that we discussed right earlier. This is, I will say, a non-solution because basically it solves a problem. It solves a precise exceptions problem because you can see that the writes are happening in order, right? The update of the architectural state is happening in order. But unfortunately, this fast instruction, add instruction, is taking as long as the slowest instruction. In fact, every instruction needs to take as fast as the slowest instruction, basically. That's the problem, basically. The worst case instruction latency determine all instructions latency. This should really remind you of the single cycle architecture and why we actually got rid of it earlier. For example, memory operations can take, I don't know, hundreds of nanoseconds, right? So does it really make sense to have each functional unit take worst case number of cycles? And the answer is it doesn't in the end. But this is a solution, not a good solution. So that's why we're going to talk about supporting precise exceptions in better ways. And the key question we're trying to answer is, how do we support precise exceptions in the presence of instructions completing out of program order? This is going to become exacerbated when we talk about out of order execution, which is going to actually do other things. But there are four major solutions to this problem. I'm going to especially focus on the reorder buffer. If you have time, I will mention history buffer. In the out of order execution lecture, we'll briefly discuss future register file. There's also checkpointing. But all of these actually are employed in today's systems. Maybe history buffer is not that employed today, but these are actually employed in existing processors. So at least 3 out of the 4 are employed in existing processors. So existing processors are actually much more complicated than what we have just seen over here. And we've just complicated this multi-cycle machine, right? Okay. So let's jump into the reorder buffer. If you want to learn more about history buffer, future register file, and checkpointing, you can certainly look at old lecture videos. Also see the backup slides. I'll leave them over there. As I said, maybe I will cover the basic idea and we'll get back to it maybe. So I think before jumping to reorder buffer, this is a great time to take a break. Let's take a break until 15 past. Okay, I think it's time to get back. So just to remind you, we're going to try to answer this question. How do we support precise exceptions in the presence of instructions completing out of order? And the first, maybe the only solution that we're going to go into depth is going to be the reorder buffer. And the idea here is very simple, except it's going to add a lot of complexity to the back end of the pipeline, as we will see. The idea is basically complete instructions out of order, but reorder them before making the results visible to the architectural state. In other words, update the architectural state in order, but store the results of these instructions somewhere microarchitecturally. And this place is going to be called a reorder buffer. Does that make sense? We still update the architectural state in order, in the program order, but the instructions will write their results out of program order and the machine will keep executing. That sounds good. So basically, we're going to introduce this thing called a reorder buffer. After an instruction completes, it writes its result into the reorder buffer. Reorder buffer is actually a hardware structure that keeps the instructions in sequential order. These are all of the instructions that are in the machine. And you only update the register file or memory when the instruction is the oldest instruction in the reorder buffer. Okay? That's the idea. So you sequentially update the register file based on the initial ordering of the instructions. And this is implemented as a circular queue in hardware. We're not going to go into a whole lot of detail, but this is how it works, basically. That's the idea. That's the concept. So how do we go into the next level? Basically, when an instruction is decoded, remember, decoding is in sequential order. You fetch the instructions in sequential order. You decode them in sequential order. So when an instruction is decoded, you have not seen later instructions yet. That's good. So the machine reserves the next sequential entry in a special buffer called the reorder buffer. That's over here. We're going to see the structure of it in a little bit more detail. When an instruction completes, meaning finishes execution in the function unit, it writes its result into the reorder buffer entry that was allocated to it. This could happen out of order. Remember the earlier picture where we showed not this. Basically, this instruction completes earlier than an older instruction. So this instruction can write its result into the reorder buffer earlier than an older instruction. But that's not a problem because reorder buffer is not visible to the programmer. Reorder buffer is a purely microarchitectural construct. Okay? So that's the idea. So when an instruction completes, it writes its result into the reorder buffer entry. It could be out of order. Now, when an instruction is the oldest in the reorder buffer, and it has completed without exceptions, and you're not going to handle any interrupts at that point in time, you move the result, or control logic moves the result of that instruction from the reorder buffer to the register file or memory. That's when you update the architectural state. So only the oldest instruction updates the architectural state. And you keep doing that for the next oldest, next oldest, next oldest. So that's the essentially, this way, you can enable architectural state to be preserved precisely. But you also enable out-of-order completion of instructions. Now, that's the good thing. You get higher performance, and you also have von Neumann semantics to be obeyed. Okay, so let's take a look at this. I'm going to show you an example of this. But this is a hardware structure. Reorder buffer is a hardware structure that keeps information about all instructions that are decoded, but not yet retired or committed, as we have discussed. So it's a circular queue in hardware. In this case, you see a 16-entry buffer. You have, as with any circular queue, you need to have pointers to the oldest instruction. This is pointed to the reorder buffer entry that contains the information about the oldest instruction in the machine, or head. And then there's a tail pointer, which points to the youngest instruction. And this can be empty, of course. And there needs to be some semantics that needs to be satisfied with empty queues. But basically, that's the idea. So you need to have entries. You need to have each entry has some fields. For example, the valid. Valid means that there's an instruction allocated to this reorder buffer entry. If there's no instruction in the machine that's decoded, then all of the entries are invalid. All of the entries are at 0. And then the next part can be the destination register ID. Which destination register is this instruction writing to? This is a value of the destination register. What is the value that this instruction wrote to the destination register? Is this value actually trusted? Meaning, did the instruction actually write this value? Because you allocate the reorder buffer entry at the beginning when you actually decode the instruction, but then it takes some time for the instruction to write the result. For an add instruction, for example, it takes some number of cycles, right? For a multiply instruction, it takes some other number of cycles. So when the instruction actually writes to the destination register, it goes and finds its reorder buffer entry because it has allocated. It knows what reorder buffer entry it has. It's been allocated. It basically sets the written bit to the destination register and it writes the value over here. This happens after the instruction finishes execution, after it gets out of the functional unit. Okay, and there could be other fields that I will briefly mention in the next slide. Basically, there could be other fields. For example, store instructions, which we're not going to deal with in this lecture. You need to have the store address, right? Because you need to update the memory also in order, in program order. So you need to have the address of the memory location that you're going to write to. You need to have the data of that you're going to write to in that memory location. This is a valid bit of the reorder buffer. Basically, is there an entry here? The program counter of the instruction that's used for exception handling. This is basically, you need to save the exception causing program counter, just like we did in the multi-cycle MIPS architecture. And then there's a field that says, did the instruction generate an exception? Because you need to record that information also, right? Because reorder buffer contains instructions that may have been executed, that may not be the oldest yet, right? Because an instruction, let's go back to this picture over here. But for example, this instruction may finish much earlier than other instructions, as you can see, some other instructions. You need to record whether it's caused an exception over here, right? And then you handle that exception when that instruction becomes the oldest instruction, if it ever becomes the oldest instruction in the machine. So that's why you need to keep all of these bookkeeping about what happened to the execution, to the instruction while it's executing in the pipeline. And there are valid bits for the register and data values. For example, is the destination register value written, meaning has the instruction finished execution? And is the store address or store data have been generated? Again, I'm not going to talk about stores and loads in this particular case, but they complicate the reorder buffer. So basically, just to summarize, you need everything that's required to correctly reorder instructions back into the program order. Update the architectural state with the instruction's results. If the instruction can retire without any issues, when it becomes the oldest instruction in the machine, and handle an exception interrupt precisely. if an exception or interrupt needs to be handled before retiring the instruction. Basically, you need everything that's needed to support this. That's why this reorder buffer is relatively large, let's say, for every instruction that's decoded but not yet retired. Once an instruction updates the architectural state and gets retired, you deallocate the reorder buffer entry for that instruction so that a new instruction can be brought into the machine by decoding. Does this make sense? Okay, good. So you need to have valid bits to keep track of the readiness of the results and find out if the instruction has complete execution. That's what the purpose of these valid bits over here are. And that's essentially what I showed over here. Destination register written is essentially a valid bit saying, has this instruction written to the destination register? And if so, then the register value over here is the register value that the destination that this instruction produced. Okay, now we're going to go through an example. But before we go through the example, what does this accomplish? What this accomplishes is this picture, basically. So what does this picture say? This picture says, these are all independent operations, basically the same picture that I showed you earlier. Everything was independent over there. The result of an instruction is first written to a reorder buffer when the instruction completes. For example, this instruction has one cycle execution. It writes its result into the reorder buffer when it completes. It doesn't update the architectural state. Reorder buffer is microarchitectural, so we have not violated the von Neumann model or precise exception semantics. But the result of an instruction is written to the register file when the instruction is the oldest instruction to the machine. That's what this write is. So you can see that the oldest instruction over here writes to the reorder buffer first, and the next cycle, there's some logic that checks whether the oldest instruction is finished. It takes the value from the reorder buffer and writes into the register file. And now you can see that the writes are back in program order. So we're updating the register file in program order, register file and memory. But we're going to look at the register file most. So then the question is, there are some values in the reorder buffer that are produced by these instructions. If there's a dependent instruction, how does it get that value? Right. Ideally, we would like to supply that value to the dependent instruction because these values are already produced so that we can make progress. That's the idea. We're going to see that. And we're going to see actually this enables a whole new world because reorder buffer is actually accomplishing something that's even more interesting than you may imagine. It's not just about reordering, as you will see. It's also about renaming the registers. And that's going to be the core of out-of-order execution. But we're going to get to that soon. So hopefully this picture is clear. Now this picture is beautiful because we have preserved the precise exception semantics, von Neumann model, but we have not given up finishing the instructions early. Let me go back to this picture where that was not true. Remember? So clearly the first one, this was not true. This violated the semantics. We fixed the problem by making everything worst case. Bad idea. Now reorder buffer fixes the problem by decoupling the sequential execution semantics from actually writing of the result. Writing of the result is microarchitectural. Sequential execution semantics is architectural at the end. So now this enables higher performance because we can enable reading of these values that are written by instructions because there might be some dependent instruction. We're not showing that in this picture, but we're going to see that soon. But we have not violated the semantics also. Okay. Any questions? Okay, so basically the question we're going to tackle now is this. What if a later instruction needs a value in the reorder buffer? And we're going to see that this is really going to happen in out-of-order execution. So the next lecture is going to really exacerbate it. For now, bear with me because I'm not going to give you maybe examples you're not going to be completely satisfied with because otherwise it'll complicate the example significantly. But hopefully you will see the idea. So basically one option will be this instruction, let's say, wrote its result into the reorder buffer. If a later instruction comes, which may be over here actually, and it needs that value because it's dependent on this instruction, what do? One option is basically stall the operation, stall the pipeline. Well, this is not very satisfying because if you stall the pipeline, fine, yes, it's an in-order machine, but the result is produced already. You can actually get it from the reorder buffer, right? Why stall the pipeline, basically? So this is not an option we're going to be satisfied with. So a better idea is basically read the value from the reorder buffer. But then this brings the question about how. And this complicates the machine a little bit more. Okay, so let's take a look at this. So how do we access the reorder buffer? So this is a pictorial view. So you have an instruction cache, you fetch the instruction, you decode the instruction, you place the instruction to the reorder buffer, and we want to check where the source registers are coming from. The source register can come from the register file. The source register may be in the reorder buffer, or the source register may come from the bypass paths. So basically, when an instruction is being decoded, there could be multiple different places where the source register, one of the source registers may be available. Or it may not be available yet, because there may be some instruction that's going to write to that register in the pipeline that has not produced the value yet. It could be nowhere. Well, the up-to-date value may be nowhere. It could be in the register file. This means that there's no other instruction that's executing that's going to write to that register, because the instruction has already written to the register file and retired. It's out of the machine. It could be in the reorder buffer, the value that you need. This means that the instruction that you're getting the value from has written into the reorder buffer, but is not complete. It is not retired yet, but the value is available. So this instruction should be able to get it. Or it could be in the bypass path, which is very similar to the pipelining bypass path that we have seen, or forwarding paths last time. I'm going to ignore the bypass path for now, but you really need it for higher performance also. But the fundamental operational principles of forwarding paths don't change based on the reorder buffer. But now we complicated the machine a little bit by adding this reorder buffer. So, okay, ignore the bypass path for now. Bypass path means that basically you can get the value immediately after it's produced from somewhere, right? Before it gets written into the register file or the reorder buffer. So it's actually a faster forwarding mechanism that happens in the back end of the pipeline. So let's ignore that. Even a register file and reorder buffer basically complicates the machine together. So register file. So how do you access, let's take a look at how do you access register files. So I'm going to introduce multiple concepts over here actually, which is interesting. By complicating the machine, we're actually tackling multiple different things. So register file is, you index the register file with register ID, which is the address of an entry. So you know this from the instruction decoding, right? This is called random access memory, which is good, right? This instruction accesses register 3. You use register 3 as the address. Now, reorder buffer is not like that, because reorder buffer, you don't query the reorder buffer using register 3, right? The instruction that's being decoded needs register 3, as we will see also. But reorder buffer is not organized like that. The reorder buffer is organized like, this is my oldest instruction, and this is my youngest instruction. This is the sequence of instructions in program order. Where is register 3 over there that I need? The register 3 I need. Well, let's go back. It's actually somewhere. It's actually encoded in this destination register ID in one of the entries, maybe. So it's actually somewhere. You can find it. But this requires a very different type of search, if you will. You cannot just index the reorder buffer and get the value you're looking for. You really have to do a search. So this brings us to another hardware structure that you have not seen before. How many of you have seen content addressable memories? Probably no one. So this is also used in real hardware. Basically here, you search all of the entries with a particular value. In this case, register 3, for example. I'm going to show you this with an example because otherwise it's very hard to understand. But basically, if you really want to get the value over here, you need to have a content addressable memory. We're going to fix this problem later on, so don't worry. But I think it's important to see the reason why this is content addressable initially. So we need to search the reorder buffer with the register ID, which is part of the content of an entry. That's why this is called content addressable. The address, the address that is actually with the instructions that are ordered with is not what you're searching the reorder buffer with. You're really searching it with some other key, and you're trying to find whether that key matches some content in each of the entries. Okay, so let's make sure this actually makes sense with an example over here. So I'm going to go through this example. This is going to be useful for the next lecture also. So please try to understand it well. Next lecture meaning out of order execution. Basically, we're going to have a register file. Register file has a val bit. Each register has a val bit, and each register has a value. Remember the val bit. We actually had a val bit. If an instruction is going to write to a register, it sets the val bit to 0, right? Because later instructions should not get that value until that value gets updated. We show this in pipelining. That's why you need the val bit. It's the same val bit, basically. And then reorder buffer also has a val bit, whether the entry is valid, whether the destination register is written, if the destination register is written, what is the value of the destination register? And this is the destination register ID that the instruction that's allocated to that entry is writing to. And again, we have oldest to youngest instruction. These are just pointers. They don't indicate it. Initially, this is empty. So initially, all registers are valid. So initially, all of these, when you start the machine, for example, all of these should be 1, and they should have some reasonable values that are loaded when you load the program in the register file. And the reorder buffer should be empty because you have not fetched an instruction. You have not decoded an instruction yet. Now let's simulate this program. Again, it's not going to be the ideal example. The real example is going to come in the out-of-order execution lecture. But this is going to prove some points that are going to be important for especially out-of-order execution, but also handling precise exceptions. So we're going to simulate this simple program, most of it at least, and we're going to see what happens to the register values. So to be able to do that, I think it's better to use this. Okay, so this looks good. Do I have enough colors? 3 colors. I don't know, maybe not. Okay, so basically, initially, all of the registers are valid in the register file and the reorder buffer is empty. Let's make sure that's the case. So initially, all of the registers are valid. 1, 1, 1, 1, 1. And initially, reorder buffer entries are invalid. Let's do that. It's kind of boring to do that for all of them, so I'm going to skip them. So all of them are 0, basically. And then the pointers need to be fixed also, oldest equal to youngest, for example. So youngest pointer needs to be there. Okay. Now, let's simulate this. Let's fetch this instruction, this multiply instruction. Multiply instruction is going to be decoded. While it's being decoded, it figures out it needs to access register 1 and register 2. You index the register file, register 1, valid, great. So there's some value over here, let's call it 1. So you take value 1, and then you also index the register file, register 2, valid, great. So there's some value that you can trust over here. So the first multiply instruction can go and execute after this. So while it's being decoded, you do this, right? You read the register file. But now we also introduce the reorder buffer. While the multiply is being decoded, you need to allocate a reorder buffer entry for it. Well, you take the first empty entry, which is the oldest over here, or youngest. So there needs to be some pointer management that you need to do also. Well, something is happening here. Okay, our pen is dead already. Okay, basically, the machine sets this entry valid bit to 1, which means that there's a multiply instruction over here. Register 3 is the destination register ID. Destination register value is not ready yet. Destination register is not written yet. So I don't care what this is 0, right? And then there's some bookkeeping that I'm going to ignore. So that's what needs to happen when multiply is being decoded. Something else needs to happen. Multiply needs to tell everyone that R3 is not valid anymore, right? So that later dependent instructions are not going to get whatever garbage value is there, right? Because multiply is going to produce that value. Right? So at this point, we've decoded multiply. That sounds good, right? Okay, so now let's decode the next instruction. The next instruction is the second multiply over here. I'm going to use red for this, I guess. So what does this multiply do? It basically first checks R3 is available? No. So it cannot execute, basically. Is R4 available? It's available. That's good. Let's say that this is 4, so it gets the value 4. That's fine. We're going to get back to this not execute soon. And then it allocates an entry in the reorder buffer. So this is the red multiply over here, just to make sure you can. Oh, you cannot see it? No, you can see it. Good. So it's going to write to register 11, which unfortunately doesn't exist over here, but it's not that important. That's why it's register 11. And then register 11 is clearly not available yet because it's being decoded. This instruction is being decoded. And it's going to basically set register 11 to invalid over here so that later instructions are not going to get the garbage value over here that's not useful anymore because it's going to be rewritten with this. Okay, so this sounds good. But let's imagine a case where, so basically later instructions are not going to get this value R3 after this first instruction wrote over here, right? Now let's imagine a case where there was some separation between these instructions, and this multiply wanted to read R3. Okay, where could this R3 be? R3 is not here because this was 0. And this multiply, let's say this instruction had written this R3. So let's assume that this multiply instruction wrote to this R3, and there's some value over here. I don't know, 1,568. I just made it up. I don't know why. Now this value is here. It's not in the register file. This means that this instruction has written it to the reorder buffer, but it didn't write it to the register file yet for whatever reason, right? Now let's redecode this multiply instruction in this new scenario. If we redecode this multiply instruction, what we do is we check R3. Is it here? It's not here. Now, if you want to check whether it's somewhere here, what do we need to do? Well, we need to basically look for whether an R3 exists earlier than this instruction, somewhere in the reorder buffer. So what does that mean? Basically, we need to search the content of the reorder buffer under destination register ID and compare whether that content is equal to R3. So we have this multiply, R3. We need to check whether this R3 is equal to, whether this value over here is equal to this 3. If it's equal, then this is the R3 we may be looking for. Not quite, not necessarily, right? Because there might be some earlier instructions, but we didn't show that over here. So you will see that later on. So basically, what you can do is you can actually check, you can compare all of the entries in the reorder buffer to the register ID you're looking for. And if there's a match, that means that you may possibly be looking for this register value. And if that's valid, then you can get this value over here, right? Does that make sense? But the problem is you need to do this comparison for all entries. Here, I gave you a cooked up example where these two instructions were quite close to each other. But if these instructions were far away from each other, there would be lots of valid entries over here, and they could be writing to R3 as well, potentially. So you need to actually, this instruction needs to find the latest definition of R3, latest instruction writing to R3 that's older than this instruction, and get the value from that. Does that make sense? So you should not get any R3, any value of R3 from the reorder buffer. You should really get the latest one that's before this instruction. Okay? So, okay, if you didn't understand it, I'm going to give you another example soon. Okay, so this is why this is content addressable. But before I move on, I should basically say that if you're searching for R3 in the reorder buffer, if you're searching for any register in the reorder buffer, actually, you need to have comparators to this destination register ID field. So this is one. You need to compare entry 0. You need to compare entry 1. You need to compare entry 2. You need to compare entry 3. Yeah, and then you keep doing that. Basically, you need to have 16 comparators that compares whether this register you're reading is actually written by any instruction over here. If that's true, then the entry must be valid, and the value must be valid, and this must be the latest definition of R3 before this instruction. So there's an ordering also, unfortunately. So it's actually a priority-based comparison logic that needs to be implemented so that this instruction can get the right R3 if it's in the reorder buffer. So this is the content addressable search. This is why this is called content addressable. I don't know if you can see that. You're searching this memory structure with part of the content that's inside the memory locations. You're searching for a particular content. And in this case, the content is the ID of the destination register, but there are also some special cases. This needs to be valid, this needs to be valid, and this R3 needs to be the oldest, youngest R3 that's older than the instruction that you're looking for. So it's really an age-based content addressable search. And this is a complicated data structure, if you will. You can do this in software. Clearly, you can do this in software. Clearly, you can do this in hardware also. And hardware exists to do that in some machines. Is this clear? Okay, good. So let's take a look at, I kind of diverged a little bit to show you the content addressable search, but let's keep decoding these instructions. Tomorrow or later today, probably tomorrow, we're going to do a lot more decoding of these instructions in a, let's say, much more methodical way. But let's take a look at what happens to add R5, R6, R3. There's something else interesting over here. This add R5, R6, R3. Okay, I think I run out of all my colors right now. When it's decoded, it basically checks whether R5 is there. It's there. That's good. It's valid. R6 is there. It's there. It's valid. So it basically takes those values. It sets R3 to 0. Well, it's still 0. That's good. So R3 is still not trusted. And then it needs to allocate another entry over here in the reorder buffer because it's being decoded. Now this entry, the destination is R3. Something interesting is happening. So another R3 came over here. It's not valid yet. Okay. So now another R3 is inside the reorder buffer. So there could be multiple definitions of R3, as you can see in the reorder buffer. But not in the register file. Register file is only one R3. But in the reorder buffer, in the machine, there could be actually many, many instructions writing to R3. All 16 instructions can be writing to R3. Semantically, that may not make sense from a program perspective, but it's possible. It's not disallowed, right? Now there's something interesting happening. This is a microarchitectural structure, and this is an architectural structure. Architecture gives you only 8 registers, right? And we said that this is limited. It's limited by the instruction encoding, if you remember the ISA lectures. But we want it larger, because if you actually have registers close to your processing units, it's faster. Well, how do we get larger? Well, this is how we get larger. Basically, this R3 is being renamed to a reorder buffer entry. Now, your architecture doesn't provide you R3s. Well, microarchitecturally, I can have many R3s because they're completely independent of each other. This R3, remember, it has nothing to do with this R3. This is a write after write dependence, if you remember, or output dependence. It's a false dependence. It's not a true dependence. The only reason these 2 instructions are writing to R3 is because there are not enough registers in the ISA. But now we've kind of overcome that limitation. We basically say, this R3 is going to be produced at this location. This other R3 is going to be produced at this location. And they're really different R3s, semantically. So this is how a reorder buffer actually enables a renaming of registers. And this is going to be very, very important in the next lecture. So that's the reason why I wanted to actually go through this. But now actually take a look at this R3. Let's take a look at this instruction. There's a reason why this sources R3 here. Now this add instruction is sourcing R3 and R8. So it looks at R3 when it's being decoded, it's 0. It looks at R8, it's 1, it's not that important. It gets the value 8 from there. And R12, it sets R12 to 0. R12 is invalid basically. And then it's allocated to this entry. It's writing to R12 and the value is not ready yet. Now, while it's being decoded, if you really want to try to get the value of R3, you need to search the reorder buffer while this is being decoded. This is 0, so the value cannot be in here. Where's the value here? Well, you need to do a search. So what R3 should this instruction get? This is this instruction over here. So it should get the latest definition of R3 older than this instruction. So it should really get the value from here, right? Conceptually. Conceptually, that makes sense. It should not get this value of R3, right? That makes sense. Then the question is, how do you search for it? Well, that's the content addressable memory, that's age-based. So whenever you actually compare this R3 value to every single location, there will be 2 matches. These 2 will match, and their entries are valid. This is valid. Well, we just made it valid earlier. This is invalid. This instruction should not get the value from here, because semantically that's wrong. It should really get the value from the youngest instruction that's older than this instruction, which is this one that's defining R3. So there needs to be logic to ensure that. And that makes this content addressable search extremely expensive. That's why we're going to eliminate it in the next slide. Does that make sense? Okay. So this example actually shows a lot of interesting things. The concept of content addressable memory, and also how to actually search for it, and how to avoid this sort of hardware, let's say. Yeah. Was there a question? Okay. Okay. So let's try to make this picture better. So I'm going to share the screen again, if I can find it. No, I need to do something else, which is in 2, I guess. Okay. Okay, that can remain there for now, I guess. Okay, so basically, we're going to get back to this register renaming. But we have an issue over here, which is we index the register file nicely using the register file ID. We can get the value quickly. But if the value doesn't exist over there, we need to do this content addressable messy search on the reorder buffer. And this is actually very hardware intensive. And as the reorder buffer size grows, in today's machines, reorder buffer size can be actually more than 1,000, which is interesting. That search becomes even more expensive. So we want to eliminate this expensive search. So that's why people have developed the idea. So how do you simplify the access to this reorder buffer? The idea is use indirection. What does this mean? Access the register file first. You don't access these in parallel. You access the register file first, check if the register is valid, and then access the reorder buffer next. And now, if you do this, the reorder buffer does not need to be content addressable if you do some things under the access the register file first correctly. Okay, so what does that mean? So if the register is not valid, register file stores the ID of the reorder buffer entry that contains or will contain the value of the register. Now we're going to actually complicate this register file a little bit to make the reorder buffer access simple. So we're going to see this also with an example soon. But basically, we're going to map a register file entry to a reorder buffer entry. If the value, so when an instruction is decoded, it checks whether the source register is there in the register file. If the valid bit is 1 for the source register, that's great. You get the value from the register file. If the valid bit is 0, the register file will contain a tag, a pointer, to the reorder buffer entry that's going to produce that value. And this way, you can directly index into that reorder buffer entry without doing this messy content addressable search. And this is how you can map a register to a reorder buffer entry. Register file maps the register to a reorder buffer entry if there's an in-flight instruction writing to the register. So let's take a look at that. Basically, we're going to add this tag to the register file. And this is going to have pointers to the reorder buffer entry that's going to produce the value for that register. So maybe we should simulate this. The same thing, but a different simulation. Okay, I'm going to go through this relatively quickly because it's going to be the same simulation, except we're going to have tags that'll simplify things. So how do we go back here? DocuCam. That doesn't work. Stop sharing. Is that better? Okay. So now let's do this. So initially, all registers are valid, the same thing, and all reorder buffer entries are invalid. Okay, you can fill the rest. We're going to decode this instruction. Multiply R1, R2 goes to R3. You get the value in R1, that's good, it's there. You get the value in R2, that's good, that's there. This instruction can execute. We set register 3 to 0, basically, meaning that it's not valid because this is going to produce the value. Now we allocate a reorder buffer entry for this multiply. And then it's going to write to register 3, that's good. And then, well, it hasn't written it yet, so it's 0. This value is not trusted anymore, but we're going to do one more thing that's critical, which is really set the tag of the register to reorder buffer entry 0. Now, what does this mean? Basically, this means that register 3 is going to be produced by the instruction that's being tracked in reorder buffer entry 0. So if anyone wants this register 3 after this, should look into reorder buffer entry 0. That's my index. I don't need to do this messy content addressable search. What I've done is I've linked all future references to register 3 to reorder buffer entry 0, telling them, I don't have the value for you. Go check reorder buffer entry 0. If it's there, take it, because that's the instruction that's producing your value. If it's not there, wait for it. It's going to produce it and get it from there. So that's the idea over here. And this is purely, there's no content addressability over here anymore. So let's take a look at how this works. Basically, this multiply now sources register 3. It now knows that it needs to wait for reorder buffer entry 0. That's great. Register 4 is available, so it takes 4. Fine. And then it does the same thing to register 11, makes it, invalid. But it sets the tag to reorder buffer entry 1, because it's going to store register 11 into reorder buffer entry 1 when it finishes. So anybody who stores register 11 should look in reorder buffer entry 1. Let's do this very quickly for the next instruction also. R5, R6, when we're decoding it, this is good. R5 and R6 are valid, so you get the values and you can execute. Now we're going to write R3. There's an interesting thing that's going to happen here. R3 is still invalid, but now this reorder buffer entry 0 is not going to be reorder buffer entry 0 anymore, because this instruction is going to be allocated to entry 2, register 3. It's not ready yet. But anybody who wants register 3 after this point, after this instruction, should look into reorder buffer entry 2, not 0. We're decoding instruction in sequential order. This instruction overwrote register 3, and later instructions whose source register 3 should get the value from reorder buffer entry 0. Now, in other words, what we've done is renaming. We've renamed register entry 3 into reorder buffer entry 2. Does that make sense? And you can keep renaming the same register many, many times this way. And this is going to form the basis of out-of-order execution tomorrow. But let's go back to finishing these slides. So hopefully this is clear. You're going to see this again tomorrow if it's not clear. Hide floating meeting controls. Okay, I need to do something else, which is this. Okay, it's the same slide. So this is real. So as you can see, this is actually Intel Pentium Pro, which is the first really commercially successful out-of-order execution processor. And you can see that this is the register file. It's called, it's called actually, this is the mapping table. This is the tags that I showed you. And these are the 8 registers. And basically, if an instruction is sourcing a register 0, this is an index that tells you register 0 is in the register file, architecture register file, or it's coming from reorder buffer entry X. So they basically separated the tags from the register file over here. But it's essentially the same concept. So what I've shown you is real, as you can see. And we're going to make it a little bit different later on tomorrow. And this is Intel Pentium Pro, which is interesting to look at because at that time, they didn't have enough transistors they could put on a chip. So they put the whole L2 cache in a separate chip, as you can see. Okay, so basically, one of the major concepts that we've covered today is this register renaming with a reorder buffer. I want to emphasize this a little bit more because this is going to be very important tomorrow. What we've done is output and anti-dependencies. If you remember them, we're going to look at them in the next slide also. They're not true dependencies. The same register refers to values that have nothing to do with each other. And the main reason why this happens is because you don't have enough register IDs in the ISA. Now what we have done is we renamed the register ID to the reorder buffer entry that will hold the register's value. That's going to produce that register. This is, you can think of that renaming the register ID to a reorder buffer entry ID. We're going to see tomorrow renaming the architectural register ID to a physical register ID. And after you do this renaming, reorder buffer entry's ID is used to refer to the register. So this is microarchitectural. This big register file or big reorder buffer is microarchitectural. It's not visible to the programmer, but underneath, we get rid of these dependencies, these false dependencies that exist because we don't have enough names. Tomorrow, we're going to introduce the term reservation station, so you'll also see that. So this eliminates anti and output dependencies. The only thing that you really need to now to deal with is really flow dependencies, which is really the true dependencies, right? And we actually know how to deal with them, kind of very linking them through these reorder buffer entries. So this also gives the illusion that there are actually a large number of registers. You may actually architecturally have 8 registers. If your reorder buffer is 1,000, internally, microarchitecturally, invisibly to the program, you actually have 1,000 registers internally. That's beautiful, I think. So remember, basically, these are the data dependence types. The only true data dependence is the first one, because you really need this value, the second instruction that really needs the value that's produced by the first instruction. These are all false dependencies. They can be eliminated using register renaming, which is a way of eliminating them without changing the instruction set architecture. So this is for you to do. Basically, you can actually do this example on your own. I've added some loads and stores also. It's basically very similar to what we've done, but for you to do. So basically, this is what we've constructed. We've constructed an in-order pipeline with a reorder buffer. What we're doing is we have in-order dispatch and execution. So you decode and you allocate things into a reorder buffer when you're decoding. You have out-of-order completion of instructions, but you write the results into a reorder buffer. You write the result microarchitecturally first, and then commit to the architectural state when the instruction becomes oldest. So you have in-order, decode, dispatch, execution. We're going to define dispatch later on more carefully. Out-of-order completion of instructions, but in-order retirement, in program order. So we're preserving the sequential semantics of the von Neumann ISA. So what happens in decode? You access the register file in the reorder buffer, allocate the entry in the reorder buffer for the instruction that you're decoding. You check if the instruction can execute. If the instruction can execute, meaning that it doesn't have any dependencies, it has the value values that it needs, you dispatch the instruction. Dispatch is basically taking the instruction and putting it into a functional unit so that it can execute seamlessly. During execution, instructions can complete out of order, as you can see, out of program order. No problem, because when the instruction completes, you write the result into the reorder buffer, which is a microarchitectural structure. You don't update the architectural state. And there's an asynchronous process. So the retirement and commit is an asynchronous process. There's a finite state machine or control logic in the back that checks whether the oldest instruction is ready to finish, basically, if it doesn't have exceptions. If it doesn't have exceptions and it's ready to finish, meaning it also already has its result generated, it writes, this control logic takes the result from the reorder buffer and puts it into the architectural register file or memory, because memory is handled similarly, except it's just huge. And if it doesn't work that way, unfortunately, if there's an exception, for example, then this control logic flushes the pipeline and starts from the exception handler, just like we discussed earlier. And that's the final pipeline that we built today. Let me quickly cover the trade-offs of this reorder buffer. Well, we have very little time left. But basically, this is conceptually simple for supporting precise exceptions. And it also can eliminate false dependencies. It can link instructions, as we will see. Unfortunately, you basically need to access the reorder buffer. It adds more complexity, clearly. There's more hardware. But it adds also complexity in the sense that you need to get the results that are yet to be written to the register file. And this requires content addressable memory or indirection. Content addressable memory is very complex. That's why we do indirection. But indirection actually increases the latency a little bit, but it's actually at least not as complex. People have developed other solutions to eliminate some of these disadvantages, but they also get rid of some of the advantages somewhat, and they complicate the system. History buffer, future file checkpointing. They're all actually the solutions that we don't have time to discuss. But again, you can see the lecture video from past years and also the backup slides. So this is the lecture video. And there's actually a lot more elaboration on it if you're interested. Okay. So if you have actually reading, Smith and Soy paper covers some of this, but probably not to the extent that we have covered today.